Excellent. We've got some emojis to start with. That's nice. It's good to see you're there. So I was at the open day today. Can anyone give me a thumbs up if you were at the open day or you're going tomorrow? It would be lovely to see you, and hopefully you met lots of our tutors already. Hey, that's great. Good news. Hopefully you got to see the undergraduate lab, speak to lots of people, got to visit some colleges, a useful experience. And you will, if you're not been today, you might get to go tomorrow. That would be great. And if not, there's one in September as well, so you don't have to miss out. Right, I'll make a start. So you're used to seeing Kat here, but Kat's away today, so you've got me. So my name's Sian. I'm the outreach manager at the Department of Physics. So today we're going to do a solutions webinar. It's the same things as usual. So just you can use the Q&A, and we'll do some Q&A as we go along. After my wonderful ambassadors are going to present lots of solutions to you. We will use the chat to talk to each other, but please do keep it on topic and keep it polite and don't share any personal details, as we usually say. So the usual rules apply. Just a little bit of a introduction in case this is your first webinar and it's the first time you're thinking about PAT, and that's fine, to give you a little bit of information. So the PAT test and the PAT prep course. So the first things first, the PAT is the physics admissions test at the University of Oxford. It's sat by all candidates for physics, physics and philosophy, engineering and material science. And your results from the PAT test forms part of the information the admissions tutors use to decide who to shortlist for interview. You must register yourself as a candidate for the PATs. This is really important. Don't rely on anyone else doing it. You've got to look into this. And this year, the PAT will be on screen and it'll be entirely multiple choice as it was last year. But the syllabus is unchanged and you can have a look at previous questions and they'll be very similar. And you can have a go at the sort of online built-in screen calculator, which you can use. And so there's a bit of a practice available. And we will send you all the links for these kind of things so that you'll get them as you're registered for the course. So that, as I said, it's required for physics, philosophy, engineering, and material science, forms part of the information we use. You need to register yourself and it'll be on screen and multiple choice. Okay, this is part of the course. I think we're on the second solution webinar, which is maybe your fourth webinar in total. Kat every week sends you the list of the schedule and you can see which one we're highlighted and you can see where we are in the programme. And we collate all this information on the webpage, which has been shared with you. So if you need to look back at any of the webinars, it's the first one you've done, that's absolutely fine. It's all recorded and available for you there. So Kat will send you that link if you haven't had it already. And that's it. And to keep up to date, this web address is the place to go. So this is where you'll find all the information about the PAT test. Make sure you've read it. It gives you all the dates that you need for when to apply, what you need to do. You need to look at whereabouts you can take the PAT because they're done at test centres, and there's test centres all across the country, all across the world. So you'll be able to travel not too far, hopefully, to get to one of these test centres. But obviously it takes a little bit of forward planning for you to register and make sure that everything is in place for the test day. Okay. That's it, really. I'm going to stop sharing and I think I'm going to hand over to Nina, who is going to go through the solutions to the problems that you were set in a previous webinar. So thank you very much, Nina. Over to you.
Thank you, Sian. Yeah. Hi, everyone. My name is Nina. I am a second-year PhD student, and I also did my undergrad in Oxford. I'm at UNIF, University College, and I'm gonna quickly show you the solutions to the first three problems of the last problems that you had, so that the other ambassadors have a bit more time for the second six problems because they were a bit more involved. Drop down your questions in the Q&A, and I'll go to them afterwards and try to answer as other people are presenting. Okay. You can see my screen and writing, right, Sian? Okay, I'm getting thumbs up. Cool. So the first problem says, consider the diagram in figure 1. Indicate clearly the position and nature of the image formed by the mirror. Draw rays corresponding to light coming from the open circle and mark the relevant angles. So with this sort of questions, first of all, there's a bunch of questions. And to get full points, you have to answer everything. So please make sure you either underline or do whatever you want, but it says indicate clearly position and nature. Whoops. Position and nature of the image, draw a rays, and then mark any relevant angle. So it's like 3 or 4 different things. Okay. So in order to form an image, we always have to cross 2 different rays. In this case, one of the rays will be coming down from our arrow. So a ray coming down and going through the mirror. So this will be our reference ray. The other rays are the more interesting bit. So looking, they say draw rays from the little dot on the object. So a ray from this spot would come down to the mirror, get reflected. So this is the perpendicular to the mirror. It has an incidence angle, a reflection angle, and goes into the eye. Right? So these are the 2 rays. Maybe they're on our here. And the first thing you absolutely have to note is that the incidence angle is equal to the reflection angle. Afterwards, as it gets reflected, it also goes inside the mirror, crosses our reference ray, and so we have the image of this open spot. Then, however, this is just one point on our object. So in order to draw the whole object, we kind of have to see what the top of the arrow, the bottom of the arrow do. So maybe on a separate diagram, maybe in separate color, just make sure everything is nice and clear. Draw a ray coming from the top. Again, it gets reflected at the same angle, so a bit sharper than the previous one, goes into the eye. And then you can extend it into the mirror, whoops, to form the top of the arrow. The same thing we can do with the bottom of the arrow with a bigger angle of incidence and reflection. Continue it into the mirror. So this is the bottom of our arrow. And this is how we form our full image. There we go, an arrow. So again, it says indicate clearly the position and nature of the image. So whenever they ask about the nature of the image, you have a couple of things you have to say. First of all, it's inverted. So an image can either be inverted or non-inverted, depending on your setup. In this case, it is reflected inverted. Then whether it's virtual or a real image. In this case, it is virtual. So what a virtual image means is that you cannot physically put a screen where the image is in order to like get a physical copy of that image. You can't put a camera lens there to take an image, to take a photo of that image because it's inside the mirror. So if you had like a convex mirror, you know how the rays get reflected back and the image is formed here in front of the actual convex mirror, this would be a real image because you can put a sensor there, a camera, and take a photo. In this case, you can't do that, so it's a virtual image. And finally, it's non-magnified. So it keeps its size. So these are the 3 things you have to note whenever they ask you about the nature of an image. Position-wise, maybe you can note that this distance is equal to this distance, so this is symmetric. Draw the rays and mark any relevant angles. In this case, it would also be useful to know that this angle here is equal to the angle of reflection as well. And this covers the first problem. I'll quickly see if there's any questions I can quickly answer. What is a reference ray? So as I said, in order to form an image, you do need 2 rays crossing. If you just have one ray, it just keeps going and you don't get an image. So in this case, one of the rays will be reflected from the mirror and going into the eye, but the other ray that I use as a reference ray is just the one that goes perpendicular to the mirror. Okay, I'm gonna answer questions afterwards in the Q&A, and people already are, but I hope this is more or less clear. Let me just quickly check. Okay, maybe how do we know where exactly to place the point where the rays reflect on the mirror? Is it some specific point or can we use any point? So I'm guessing you're referring to this point. Well, this is defined by first this point here, and second, like the center of the eye, say. And because those angles have to be equal, you can only place this point in one place. But when you're drawing a diagram, it's just more or less where it would be. But physically, there is only one place where this point can exist. Okay. So question 2, we have a parallel-sided slab of medium B. So again, draw diagrams. It's very useful, even if you can kind of imagine the answer. Please make sure you don't make mistakes because you haven't visualized the problem. With refractive index NB is sandwiched between two slabs of medium NA on each side. A beam of light passes from A through B into A again. So it's coming from A. And if the beam is incident on B at an angle theta to the perpendicular, the normal, what is the angle to the normal of the light beam in A after it has left B? So here. So as we know, let me draw this a bit more properly. And B, you have something coming from A at angle theta. It gets refracted at some other angle. Let's call it theta B. It reaches the other side of the slab. And it gets refracted again. And the question is, what is this final angle? So there are again 2 key points here. The first one is the alternate angle rule. Which means that because this normal here is horizontal, it's parallel to this normal here, that means that this angle is equal to this angle. So either note down alternate angle, just label them equal, and so on. And then the second important thing is Snell's law, which you'll be using a lot in any optics question. So Snell's law says that at any interference and any line between medium, the refractive index times the angle, the sine of the angle, equals the product of the refractive index times the refractive angle in the other medium. So in this case, what we can do is we have 2 boundaries, and at each boundary we can write an equation. The first one will be this. And then at the second boundary, we have this equation. And we're looking to find this angle. So as we can see, these 2 elements are the same. Therefore, we can combine those 2 and say that NA times sine theta we know, or given it, equals NA times sine the angle we're looking for. cross these out. And we can say that the two signs are equal. An important note here, if two sine functions are equal, that doesn't necessarily mean that the angles are equal, because sine of 45 degrees is the same as sine of minus 45 degrees. But in this case, the angles go between 0 and 90 degrees, which means the sines are just increasing. They go between 0 and 1 as the angle increases. And therefore, the only possible conclusion from this is that theta equals theta final. And this is our answer. So if we go back to the question, again, read whether they want you to explain something or write something down. In this case, they just want you to give the answer, which is B. Okay, so this is the second problem. Again, I'm going to quickly check the Q&A. Thank you to everyone for answering questions. Okay, we'll answer those in a little bit because they're not super specific to this problem. Obviously, things can come up, but yes, I hope this is more or less clear. And then finally, the third problem we have is a parallel beam of monochromatic light initially traveling in the direction above the horizontal enters a region of the atmosphere in which the refractive index increases steadily with height. Which of the graphs in figure 2 represents the path? So already you can see that your graph has to be height versus horizontal distance. So I'm going to label it H and horizontal distance HD. And in vacuum, so if we didn't have that changing atmosphere, the light would be traveling, as I say, above the horizontal. So something like this, right? This would be the path. So they're asking you if the atmosphere is with changing refractive index, what would the path look like? So in any situation where they ask you about a general gradual change, it's very useful to visualize the change in steps. So in this case, what we're going to do is we're going to break down the atmosphere into small slabs. So this is the atmosphere, and they say the refractive index increases with height. So this is height. So we will have refractive index 1, refractive index 2. The light is initially coming at some angle. It gets refracted, and then here it will get refracted again. So the question is, what direction is all of this going to be happening in? So I'm just going to draw a general ray. So this is theta 0. This is theta 1. So we want the relation between those two. Okay, maybe I didn't need this, but anyway. Again, you'll always need Snell's law. And in this case, you can use it as refractive index here times the angle here will need to equal refractive index here in the slab above times the angle in the slab above. So this is our incident angle, which is like given in the problem. So we can express the new angle as n0 over n1 sinus theta 0. And the thing is, because we know that n0 is smaller than n1, the refractive index increases with height. That tells us that n0 over n1 would be smaller than 1. Therefore, sinus theta 1 would be smaller than sinus theta 0. And again, because the angles are between 0 and 90, so the sine is just increasing. Everything is linear. This means, whoops, that the new angle would be smaller than the old angle. So each time light goes into a layer above, it goes closer to that perpendicular. And here it goes even closer to that perpendicular and so on. Okay? And so they ask you to choose one of those diagrams to show which one it is, and the two which go in the right direction are those two. So now you have to decide, oh, can the ray of light start going backwards? Well, sinus theta 1 will always be bigger than 0, right? Um, yeah. Sinus theta 1 will always have to be bigger than 0, therefore theta 1 will always be bigger than 0, and this cannot go, like this angle here cannot go to 0 so that it goes back on this side, right? It has to stay on the right of the normal. And so this tells us that B is the right answer and not E. Okay, so look at the Q&A. Don't we already know that the refractive angle is smaller because the question says the refractive index increases with height? So this is a very good thing to remember in general. Yeah, I think this is the last thing I'm gonna say, and then I'm gonna just type out the answers. When you have a refractive index with two media with different refractive indices, like here, I imagine a car. If we had N3, as the car with its two wheels, it's coming here. This is a denser area, right? And so this wheel starts slowing down before this wheel touches this side. So the horror car, as it's coming, it goes into the gravel and shifts towards the perpendicular. So this is just something to remember, or you can just remember that higher refractive index means smaller angle, but it'll help you with timed exams like the PAT. So if you just know that, go for the answer. That's perfectly fine as well. You don't have to do all of this, but this is why this is like that. Okay. Cool. I think this is it for me, and I'll pass over to the next people.
Yeah, okay, I'm just going to share my screen. I hope you guys can see my screen now. Yeah, so let me briefly introduce myself. So I'm currently a third year undergraduate student at the University of Oxford, and I do physics, of course. And I'll go through question 4, 5, and 9, I believe. Okay, so let's start with question 4. So it says we have a narrow beam of light is incident normally upon the same slit. The light that passes through is spread out by diffraction. And we are given a graph. And then the same slit is immersed in a container of water. And the beam of light is shown through the water and is again at normal incidence to the slit. The spread of the diffracted beam of light in the water will be the same or less or more spread out than in the air. So for this question, if we compare the light when it travels through water and air, we know the main difference would be the refractive index. And we know that the refractive index of the water is larger than the refractive index of the air. And we also, let me just type, and water should be larger than air. And we also know the relation between the speed of a wave compared the relation between speed of wave and its frequency and the wavelength of it, which would be its speed equals to its frequency f multiplied by its wavelength. And when a thin light ray or like whatever, it could be other types of waves, travels through the medium. The frequency travels through different mediums. The frequency will not change. And what changes is the speed of it. And the way that its speed, the wave speed changes with respect to the refractive indices of different medium would be the velocity or the speed of the wave equals to the light speed divided by the refractive index of that medium. So that's why we say in free space, the speed of light is the highest, which is approximately 3 times 10 to the power of 8 meters per second. But if we set our medium to, let's say, water or glass, then the speed of light in those mediums would actually decrease because of the higher refractive index of those mediums. Okay, so now we have the 3 most important equations, and let's see how well this changes the wavelengths of the light in water and air. Because of this equation, we can see the velocity of light in the water would be smaller than the velocity of light in the air because the refractive index of water is larger. And if we substitute this relation to the second equation, and remember that the frequency of the wave won't change, we have the wavelength lambda in the water would be smaller than the initial wavelength. Okay. And because of the smaller wavelengths in the water, we can finally conclude that the light in the water will be less spread out than in the air. So the answer should be C. Is there any question? We look at a way to derive Snell's law through the lifeguard problem, maybe at the end of the session. The derivation of Snell's law, I think if we have time, we can go through that in the end. But let's just go through the questions first. Why does the smaller wavelength cause less spread out diffraction? So for a wave that's being spread out, like a propagating wave, the way that it propagates is like this. So those curved lines are the wave fronts, like the wave fronts being connected together, and their separation will be the lambda of wave. And since we have a smaller wavelength in water, we therefore have a less spread out diffraction. Does that make sense? if the wavelength changes that of frequency, does it mean the frequency is a more fundamental quantity that wavelengths for waves? Yeah. It's a great way of understanding it. Because when let's say a thin light travels through a different medium, its frequency doesn't change, but its speed and also the wavelength does. So let's continue to the next question. For question 5, figure 4 shows two mirrors, X and Y, and a solid object with white spots at P and Q. So we know that P and Q are acting like light sources. So for the first part, an observer at A sees an image of P reflected in mirror Y. And we need to firstly mark R, the position of this image, and draw a ray from P to the observer at A. So I believe this question is relatively easy. So we have this mirror Y and the light source at point P. So firstly, to find its reflected image in the mirror, we draw a perpendicular line from point P, perpendicular to the mirror Y. And it's actually the bisector. So which means the image will located at the same distance as point P to the mirror Y. So this point would be the image, and we mark it as R. And draw a ray from P to the observer at point A. So we simply connect point R with point A, and well, this part, I mean, the parts that in the mirror should be dashed line because it's like virtual. Yeah. So this blue straight line would be the light ray that's being reflected by the mirror Y to point A. So the incident light ray would just be the connection between point P and the point of reflection. So it goes this way. That's it for part A. And part B actually is quite similar. It's in which mirror would an observer at point A see an image of spot Q marked as the position of this image? So you know that Q is located here, and it would be reflected by both mirror Y and mirror X. But for mirror X, if we use the same method as part A, we can see that the reflected light ray will go this way. So it's not what we are aiming at, because we are looking for the observer A who sees an image of spot Q. But again, we can start by finding the reflected image. So again, we draw a perpendicular line starts from point 2 and goes through mirror X and find the reflected image at this point. And if we can find a straight line that connects point A and this image, then it means the observer A is able to see the image of Q. And we just clearly we can do that. So let me try to change the color of it. Yeah. So light rays in red will be the light ray that starts from point Q and being reflected by mirror X to observer A. And S would be the position of this image, which is at this point. And for the final part of this question, an observer at B can see an image of P resulting from reflections at both mirrors. Draw a ray of light from P to B, which enables this image to be seen. Okay, so from the question, we can see that we need the light from P, which being reflected by both mirrors, and finally arrives at point B. So it should be something like this. Like this way. But to draw it more clearly and more accurately, of course, we need the position of the reflected image. So we start from point P, and it's being firstly reflected by the mirror Y at and the reflected image is located at point R, and then it would be further reflected by mirror X. And we have a second reflected image. And let's call this R prime, for example. And after that, we can connect the second reflected image with the final observer. I'm gonna do this in green, goes this way. So from this straight line, we have located the point of reflection at mirror X, which is at this point. And if we connect the first reflected image R with this point of reflection, we arrive at the second. So the final light ray goes from point P to this point of reflection, and it's being reflected to a light ray that goes this way, and it's being reflected again at this point, and finally arrive at the observer B. Also, just a small notice. So when you're trying to draw the light rays that's being reflected, make sure that the angle of incidence equal to the angle of reflection. So it's better to have those dashed lines, which are the normals, and you can integrate.
We lost Yuji. Hi. Just wondering if Yuji is around. Are you back on? Excellent. We lost you for a second there. It might just be worth repeating just the last thing you said. Is that okay?
Yeah, sure. I'm sorry.
That's okay. No, we're all back. Thank you.
My internet wasn't stable at that time. Yeah. So the final bit, which I'm not sure where should I start, but just a final like a reminder when drawing this type of like light ray graphs. A thing that you should do is to make sure that you label the angle of incidence is equal to the angle of reflection by indicating, let's say, for example, for this part, we can label both the angle of incidence and angle of reflection to θ1 so that it's more clear that these two angles are equal to each other. Yeah. Okay. Any question with problem 5? Okay, nice. I think I can go through question 9 for now so that I don't have to like reshare my screen after. Hey. Okay. Yeah. So let's look at, it's probably the longest question. It's actually not that hard. So it says on roads, devices known as cat's eyes are used to reflect lights from a car's headlights back towards the driver. And these are loosely based on how light that enters the cat's eye will be reflected back out in a similar direction. So the eye will often seem to glow at night. And one type of cat's eye is created using a sphere of glass with a curved mirror over half of its surface. Light entering the sphere is reflected off the mirror and exits the sphere, traveling in the exact opposite direction to its direction of travel before entering the sphere. And we start with a sphere and an angle of incidence. And also we know the refractive index. So from Snell's law, n1 sine θ1 equals n2 sine θ2. We can directly calculate the angle of refraction inside the glass. But there is a little bit tricky part in this question because the question is actually asking for the angle of deviation at the first surface, not the angle of refraction. So the graph should go like this. I think I somehow cannot paste the graph directly. Never mind, I can draw it myself. Let's start with the view and the normal at a specific point. And we have an incident light at an angle theta I, and it's being refracted because of the difference of refractive index between air and the glass, theta R. And we're looking for the angle of deviation. So the way that we do this will be if we extend the initial light ray, the incident, incident light ray, and this angle, delta, would be the angle of deviation. So let's write down the equation. From Snell's law, we know that N1, which would be the refractive index of the air, which is just 1. We usually assume this. So 1 multiplied by sine theta 1, which is the angle of incidence, which would just be 4.58 degrees, equal to N2, which is the refractive index of the glass, 1.54 multiplied by sine theta R, the angle of refraction. So clearly we can solve this equation directly by using your calculator. And the final answer to part A, the angle of deviation, delta, would be the initial incident angle, 4.58, minus the angle of refraction, which should be around 3 degrees, and more accurately 2.7 degrees. Yeah, so 1.61 would be the angle of deviation when the light first enters the glass. Okay. And for the second part, consider an idealized version of Cat's eye, whereby entire sphere has a refractive index n. The deflection of the beam inside the sphere will depend on its refractive index. And theta I is the angle of incidence of the beam, and would just be this one. This is theta I. And theta R is the angle of refraction as the beam enters the sphere. What's the total deflection of the beam once it has emerged from the sphere, assuming it only reflects from the mirror ones? So if we continue with this graph over here, the light ray will go this way, and it will be reflected at this point. we know that there's a mirror over here. So it goes like this way, and then finally being refracted out of the sphere. And we are looking for the total angle of deviation. So there will be three angles. This point is the first time when the deviation happens, and this point will be the second, and this point will be the third. And it's being refracted out. So it goes this way. Okay. So at the first point, the angle of deviation, we've already deduced it. But if for this part, for part B, it's not given, I mean, the specific value of theta I is not given. So we have to use the lattice theta I itself instead of the specific numbers. So delta 1 equals to theta I minus theta R, and delta 2, which is at this point, and the angle of deviation of this point would be this whole large angle, which is a full circle, 360 degrees, minus 2 times the reflected angle. Theta R. And finally, delta 3 will be similar as 0.1. So theta I minus theta R. And since we're looking for the total deviation, so we sum all the three together. Let's delta total would be, oh, there should be 2 at this point. Will be the sum of the 3, and it 180 plus 2 times theta I minus 4 times theta R. Check. I think it should be 16%. Yeah. So here we have derived total angle of deviation in terms of theta r and theta I. Assuming theta r and theta r are so small, so we can approximate sine theta to be equal to theta. And we're looking for the specific refractive index for the beam that has left the sphere to be in exact the opposite direction to the beam before entering the sphere. So in this case, we need these two lines, the initial incident light to be exactly parallel or anti-parallel to the light that leaves the sphere. So that means we need the angle of deviation to be 180 degrees. So if we substitute this to the total,
Just to Yuji again. Let's just wait a minute, see if she comes back. Okay. I guess what might be handy is if Katie and Nina, if you're sort of ready to go, if we have lost Yuji.
Yeah, I can start mine.
What should we say? Was she close to the end of the problem? Is that all?
Yeah, she was nearly there.
Oh. In the Oh, here we are, maybe. Is this yours, Katie?
That's mine. Can you see
Okay.
that?
Yeah, let's make a start then. I will message Yuji that we're just gonna go on, and Katie, if you want to start your problem. Thank you.
Okay, so I'm going back to question 6. So before question 9. So this one's about light, well, not waves in water. So don't be thrown off by the fact that it's not light waves. So you can do a lot of the problem with the same skills you've got from other examples. So the first part of the question gets you to look at this, it gives you a diagram and it gets you to explain what's happening to the wavelength, the frequency, and the speed as the wave enters the water. So straight away we can say that the frequency stays the same because the frequency is determined by the source and not the medium that the wave is traveling through. So even though the medium's changing, the frequency of a wave will never change. That's like if you shine a colored light into a glass block, the color of the light doesn't change. So since color and frequency is related, that never changes when it changes medium, which is quite useful to know. And then, as we can see in the diagram, the sound wave bends away from the normal as it enters the water. So this tells us that it actually speeds up. If you think back to Nina's analogy with the car driving, if you go into a less muddy area, then the wheels will speed up as it gets easier since it bends away. So it bends away from the normal. This tells us that V increases. This is different to light, since normally when it enters water, it slows down. This is because sound requires a medium to travel through, and water is a more dense medium, so the particles are closer together, so it's easier for the sound wave to be transmitted quicker. This is different to light. The sound of speed in air is about 330 meters per second, but in water, it's about 1,400, so it does increase. So we're going to go back to this equation, which is a really important one. So we're saying that F is constant and V increases, so we can infer that the wavelength must also increase. So wavelength increases as it enters the water. So that's all using this diagram. So then the next part of the question, section B, gets you to talk about how you could ever get destructive interference from the speaker. So you're going to get destructive interference at any point where the waves from the two speakers interfere at a point where one is at a peak and one is at a trough. So you can see here, they're starting in phase. That's crucial to add to your diagram, that they both start. Here I've started them both going up, increasing from the wave, and they're the same wavelength. So these are the same wavelength waves that I've drawn here. But since one is traveling a slightly further distance than the other to reach to this point, it doesn't matter where you've drawn your point as long as it is a point where you get destructive interference. Then you can see that this point here corresponds to like this point of this wave. And then the bottom wave has to travel a little bit extra in order to reach this point, which is where we're measuring. Oh, it's not supposed to be an arrow. And then here is just a sort of what that situation is at that point. So you have the wave from the top speaker and the wave from the bottom speaker, and they are exactly in antiphase. So when you add them up, you just get a resultant wave that's nothing, that's destructive interference. And when it is completely nothing, that's what we call complete destructive interference. So that happens when the path difference is a half integer multiple of the wavelength, i.e. one of the waves has traveled half a wavelength more. Or it could be 1.5 wavelengths more, or anything like that. Anything which is going to get this overlapping peak and trough at this point we're measuring. So that's what I've written here, that the path difference is an integer plus a half of the wavelength. So this is the same sort of idea as saying that the phase difference is a half integer multiple of 2 pi. We're just using distances here and the wavelength instead. So then part C gets you to work out what's the maximum wavelength that you could get destructive interference from this speaker. So we're given that it's a single frequency and the separation. So we just drawn a diagram here of the two waves coming from the two speakers, and these are the two different paths. So you can see that from this point to this point is going to be the same distance as from this point to this point. So the extra bit of wave that the bottom one has travelled is just equal to this distance here, which I've labelled as d sine theta, using this triangle. I assume that this is something you've come across before, of having the triangle and approximating as where the theta is. So, I've got a question. So does destructive interference only occur when the peaks of one align with the trough of another? So if they're out of phase, but it's not completely the opposite alignment, there'll still be interference, and it could be destructive interference, but you only get complete destructive interference when the peak of one is at the trough of the other. So you'll get some sort of a messier interference where you'll still get a wave, it might be a smaller wave, if it's just simply out of phase. But you get complete destructive interference, which is what this question is asking about, especially in part C. Yeah, so you do get something, it won't be completely down to 0 intensity unless it's the peak of 1. And yeah, it's the position of the sources of the speaker that causes this path difference, because they aren't at the same point. Is it okay if we drew this using wavefronts instead, then plotting points where the waves intersect and drawing a line? Yeah, so you could draw it as wavefront, like the lines of wavefronts instead of a wave. That's fine to do. And then showing where one is at a peak and one is at a trough. I just like this way, since it really shows that one is at a peak and one is at a trough. But anything that's clear, showing what you're doing, that's fine. Ooh. Close the Q&A. So back to part C. So this extra distance is d sine theta, and that's what we want to equal a half integer multiple of the wavelength. So for the maximum wavelength, I'm just going to say that this is lambda over 2. Say, because if I was to put a bigger value, this is saying that n is 0, basically. If I was to put a bigger value of n into this equation, it would mean that my lambda is going to be smaller. So we're looking for the maximum lambda. So I just say that n is 0, and so d sine theta, which is my path difference, delta L, is lambda over 2. And then rearranging that, you get that lambda is 2d sine theta. And the maximum possible value that this could be is when theta is 90 degrees. So that's when lambda is equal to 2d. And the orientation in this case is when it's completely perpendicular. So something like this of theta is at 90 degrees. And you have the two sources, and one is just simply, so lambda is 2d. So this distance between the two speakers is d, is going to be a half wavelength. So the first wave completes a half wavelength before even reaching the second one, and then they are completely in antiphase, if my diagram was drawn a bit better, and then reach at this point where one is at a peak and one is at a trough. So you get complete destructive interference at this point. You get other points of complete destructive interference as well. This is just for the maximum possible wavelength. Do we have any questions about that if I get the Q&A up? So someone says, but wavelength does change, so color will change as well. So color depends upon frequency, not the wavelength. So the wavelength does change, but then that doesn't mean that the color changes. The frequency stays the same, so the color doesn't change. Let's move this down. Okay, so we're going to move on to question 7 now. So the first part should be something that you've seen before, so intensity and how it changes as you move away from the source. So if you think about a source and then it's emitting in all directions, and then that in this case, light is emitting over a surface area of a sphere. So it's spread out equally because it's emitting equally in all directions. So if it started at a point in the middle and then it's being spread out over the surface area of a sphere, we can think about dividing by this area to work out the new intensity at this distance. So the original intensity we often call I naught as what the intensity is at the start or something. And then if we divide by the surface area of a sphere, and we know that that's 4 pi r squared, we get that the relationship is that I is proportional to r to the minus 2. So this question is basically asking what's the power? And in this case, we can say that n is equal to minus 2. So this you get a lot with gravitational equations and electrostatic equations, things like that. They all follow this inverse square law of intensity. So yeah, just due to the surface area. So the next part, don't be thrown off if it's an equation you've never seen before, because this looks like quite a complicated equation, but you just need to use dimensional analysis, which is a really useful tool for lots of questions. So you're not expected to understand this equation or use it. You just think about the units and things like that. So straight away, I'm replacing the proportional sign with equal to and a constant. Since we're using units, we don't care what this constant is. It'll just be a number, since we said it's proportional. So we've got that our intensity is equal to a constant, which is dimensionless, times the I naught, which is also an intensity, times all these other factors, which are all of units of distance and length, times by this 1 plus cos squared theta factor. So anything with coses and sines is dimensionless, and 1 is dimensionless. So this thing in brackets is dimensionless. We've got on our left-hand side units of intensity, and on our right-hand side, we've got units of intensity times length to the power of m, length to the power of n, and length to the power of 6. So that's what I've written here. So you know that wavelength has units of distance, so it doesn't matter what they are, whether it's meters or anything, that's all going to cancel out. The r is the distance, also has units of length, and the alpha is a measure of the radius, so it's also going to be units of length. So if I rewrite i's here, oh, that's not a very good job of it. You can imagine that there's units of intensity on each side. And this will be the right-hand side of the one above, and there to the power of 1. And this will be the right. So this L to the 0 is what I've got here with just the I. And then this is the L to the M, L to the N, L to the 6. And we know that that equals 0 since there's no L on this side. So we can just look about saying this M, this N, and this 6 must equal 0, since the units on both sides must be equal. It tells us that it follows the same relationship as above. So we know that N is minus 2, since we did that in part A. So we're given that M minus 2 plus 6 equals 0. So therefore that must mean that M is minus 4. So you wouldn't be expected to have a physical intuition of what this equation would be or anything like that. Just using units, dimensional analysis, things like that are really useful tools. And you can understand a lot about a problem just from thinking about what the units have to be. So if I go to Q&A. So in the second diagram, the waves were drawn vertically because the theta that we got was 90 degrees. So you could rotate the whole speaker situation and have it going horizontally, but they just need to be sort of along the line that joins up the speakers. It can be above as well, that's completely fine. Yeah, if you get comfortable with drawing waves different directions, turn your page if that helps, just because this is still a peak and a trough, even though the waves are going vertically. Okay. Any questions about question 7? So how do I go from m plus n plus 6 equals 0 to m minus 2 plus 6 equals 0? So we've already found from part A that n is minus 2 using this here. So we know that n is minus 2, and we're told that the relationship between the intensity of the scattered light with the distance from the scattering particle is the same as for a point source. So we're given that we can use n from above. So that's how we get to that jump in that step. So the units for intensity would be something like an energy per meter squared, but we don't need to know that for this question. So it would be like a watts per meter squared or something like that. So let's go on to question 8. So again, this is quite a tricky question. So it's really helpful to draw a diagram, just see what the situation is, draw your rays with arrows and label all your angles, because there's lots of angles in this question. So let's try not to get confused with the angles. So the setup is we've got a glass prism of 45 degrees and it's sitting on Mercury. So straight away, we can just say that's basically like there's a mirror at the bottom of this prism. So it's just going to reflect off the Mercury and almost like total internal reflection, but it's just reflecting off. So we don't care about the refractive index of Mercury because it's not clear. So this is the diagram that I drew. So you've got the incoming light, we're going to say it's at a distance x above the Mercury, that enters into the glass, and straight away we know that this angle of incidence is 45 degrees just from the setup of the question. So because this angle will be 45 degrees, this is 90 degrees, so this is 45 degrees. And then it refracts as it enters the glass block, since the glass has a higher refractive index. So I'm going to label this my theta r, and it travels through the glass block until it reaches the bottom, at which point it reflects. So I'm just calling these angles delta and theta. And then it reaches this point again. So I've just drawn the diagram for the limiting case, the extreme case of when it just comes off at a height h, because we want the minimum height it has to enter. So I've just drawn my ray coming out slightly above just basically on the level of the Mercury. And again, so since all of these angles are the same, it's going to hit the glass interface at the same angle as before. We could think about this is still 45 degrees, this is still delta on each side, this is 45 degrees. So by similar triangles, you can say that this is also theta r. And again, this comes out at an angle of 45 degrees. So spotting that at the start can be quite tricky since you don't know where your angles are, but just noticing that they're the same. So look for any symmetry in problems like this. So that's what's happening with our light. So straight away, we're going to try and work out what this theta r is. So we know that the refractive index of the air is 1, of the glass block, it's 1.4, and you're given the angle of incidence. So we just work out our angle of refraction, and that's 30.4 degrees. So now I'm going to draw these triangles again. So this first one is this left-hand triangle, which is this point to this point to this point. And then later on, I'm going to use the right-hand triangle, which is this triangle. So this is our first left-hand triangle. We've got 45 degrees from the corner of the glass block. We've got this, which is made up of 90 degrees from 90 degrees plus the 30.4 degrees is this part here. If we draw I don't think it's going to draw. But so it's 90 degrees from in between the interference and the interface and the normal line, and then the 30.4, which we worked out earlier. And then using the 180 degrees in a triangle, we can work out that delta is 14.66 degrees. So that's this angle here. So now we're going to use this in our right-hand triangle. So again, it's all the same angles, but different heights. So we're going to say that it comes off at height h, since we want the extreme case. We're going to say that this is height h. And I'm going to call this B, this point that it reflects off to this corner, I'm just going to label as point B. And we're going to solve for it and use it eventually to get x. So, and now I'm going to try and work out what B is. So I can label this side length from this corner to this corner as h over sine 45. That's just using this triangle. 1, 2, oh, that's not a triangle. 1, oh, it is a triangle. 1, 2, that's using that, and knowing this is h and this is 45. So I can label this as h sine over sine 45. And then using the sine law of a side over an angle is equal to the other side over the other angle, so this law here, I can say that h over sine 45 divided by the equivalent angle, which is 14.66, is going to be equal to b over sine of 120.34. And then we know what h is, since it's 2.5, it's given in the question, and we can solve for b. So now we know the point at which it reflects off the bottom of the glass block. Is there any questions about that? So how does h cancel out in this part? So we don't need h to cancel out, we're given what it is, so that's okay. So now we know what b is, we can think about similar triangles. So these two triangles have all the same angles. So the ratio of their sides and their heights must be the same. So I'm just saying that so that this distance is going to be my L minus B. Oh. L minus B, that's not a very good B, or L. So, and this is going to be H plus X. So I'm going to say that the ratio of L minus B over H plus X is going to be equal to whatever it is for this triangle. So here, B is my base and H is my height. So I'm just saying that L minus B over X plus H is equal to B over H. And then rearranging this for X, I have all these other numbers now because L and H are given in the question. We've worked out what B is from the angles. So we can just put in all our numbers and get that X is about 4.33 centimeters. So that's the height off the surface of the Mercury that the incoming lights must shine in order to be reflected out above the surface of the Mercury. Does anybody have any questions about part A? That's okay, we can go on to part B. So now we're replacing it with a liquid which doesn't reflect like mercury does. So it's placed on top of a different clear fluid of the same density and floats. So the fact that it's the same density is important because it means it's going to sit at the same height in the water. The same amount, H is going to be the same, basically, is what the same density tells you. And it's floating. So now you want what's the maximum refractive index of the fluid that will allow light to travel along the same path. So it's basically asking what's the maximum refractive index where we can get total internal reflection at this angle. So we know all the angles already, so it's just plugging them into the total internal reflection and critical angle formula to work out what we want. So this is just the bottom of the surface of this block. So we know that this is 1 point. If it's not going to draw nicely, but this is 1.4 n above the interface, and we're trying to work out what n is below it. So we know all our angles. We're going to say that since we want the maximum, we're going to say where this is the critical angle. So we're going to say that theta critical is 75.34, where this has just come from working out what theta is based on 90 minus 14.66. And then we're going to use the fact that the n of the glass times sine 75.34 equals n of the liquid times sine of 90 for this total internal reflection condition. And then we can just work out what n of the liquid is, and we get that it's 1 point there should be a point there. We just get that it's 1.4 times sine 75.34. So we're left with 1.35. That's not a very good decimal point. But you know, okay. We're left with 1.35 as our maximum refractive index. So we know it must be less, since we only ever get total internal reflection on a boundary where you're going from a more dense medium to a less dense medium. So we know it must be less than 1.4. So this answer makes sense. Yeah, anybody got any questions about any of these questions? No, if that's all okay, I'll hand back to. Did Julie want to finish the last part of her question, or?
Hi. Thank you very much, Katie. So that's all of our questions apart from the little bit at the end from Yuji. Is that right? Excellent. Well, if Yuji, if you're free and can get up your answer, then maybe we could do that to just finish off.
Oh, someone said, could part A of question 8 be explained again? So I'm happy to go through it again if people want that.
Yeah, okay, let's do that. Let's go through that. Thank you.
Go through it a bit slower. So can you see my screen?
Yes.
Yeah, okay, great. So the hard part of this is keeping track of all your angles and all your different distances and things like that. It never tells you that you need to assign a new variable to B. So quite often the PAT questions lead you through it less than A-level questions would. So it's just thinking of what techniques could you use. So first of all, getting the diagram is important. I think this question would be quite a lot easier if they gave you this diagram. So think about all the words that they've used. So they give you without the light ray. You know that it enters parallel, so straight away we can draw a parallel line that then hits the interface, and we know it refracts. We're looking for reflection, so we know it must hit the bottom and then come back up. So think about all the rules that you know, so refraction, Snell's law, and reflection. And just using those two rules, you can label up this diagram with all your different angles. So spotting that this is 45 degrees is also can be tricky if you just think about what you do know. So you know that this is 45 degrees here. So therefore this one must be 45 degrees and then this one must be 45 degrees. So we know it refracts, so it's going to go closer to the normal. So that's what theta r is less than 45 degrees. And then it travels down and then bounces up again. So we've got our diagram set up. Now we want to try and work out what some of the numbers are. So the first thing that we have all the information for is theta r. So just using Snell's law here, we're got to theta r using 30.4. And now we're just going to do some triangle geometry to work out other angles. So using the triangle 1, 2, 3, that's this left-hand triangle. We know what theta r is, so we add that to 90 to get the whole angle of this top here, plus 45, and then whatever's left to make it up to 180 must be this bottom angle. So that's this delta here. And then we must know that theta must be 90 minus delta, since that's a right angle. So we have a triangle like this, and we know it's the exact same triangle on the other side, just flipped. So the ratio of heights must be the same for both triangles. So we get to B just using one of the triangles. So we say that h over sine 45 is this side from using 1, 2, 3 as a triangle. And then labeling that side over this angle, say equivalently A over sine A must be equal to B over sine B, which is B here over sine of 120.34. And then we get the B is 12.06 centimeters. And it's good to do a sanity check at this point. So we know that L is 45 centimeters. We know it must be closer to the side where it comes out, since it's coming out at a smaller height. So we're expecting it to be smaller than 22.5 centimeters, which it is. So, and then this is just using our ratio of similar triangles. Say the height of one divided by the side of one triangle. If you then do the height of the other, or this is the base divided by the height, must be equal to the base of the other one divided by the height of the other one, since they've got all the same angles, they're the same triangle, just scaled up. so the ratio of their sides is going to be the same. Then we rearrange for x, plug in our numbers, and then we get x. Is there any specific parts about that? So how do you know that they're similar triangles? So we know from the question, we know that both of these angles in the corner are 45 degrees. We know that the angle delta must be the same since it's reflecting, so they must be the same angle. And these two interfaces are equivalent, basically. So you know that it's 120 degrees at the top for both of them, since this is theta r plus 90. Over here, we've got 90 in this corner plus theta r again. So you know that all three angles are the same. And if all three angles are the same, they are similar triangles. They're basically the same triangle, just flipped and scaled up on one side. The two b's used in the ratio are distinct, right? So here this is just the general sign law. This isn't talking about this question in particular, but it could be. So this is the angle, B. So the capital letters here are used for angles and the lowercase one are used for sides. Aren't you assuming the height the ray leaves at is h by using h in the diagram? Yeah, so we want the maximum height, the minimum height that it could enter at. So I'm going to assume it leaves at h. So if it would still reflect off the bottom if it came in at a higher height and left at a higher height. But since I want the minimum, I'm going to assume it leaves at height h. So why has sine 45 been multiplied by... So here, I'm saying that my side length A is this side length from the top to this corner, and A is h over sine 45. So that's where this part of this comes from. And then I need to divide by the angle that's opposite it, which is this. So I divide by sine 14.66. So that's where those two angles come from. So someone said the L minus B. So
question, excellent. And then we'll round up, Katie. Thank you.
Okay. So you know that these B's are the same since the whole thing is L, the bottom of this triangle is B, and this is just whatever L minus B is. So the B's are the same. Okay.
Awesome, thank you. I think it's a good place to start. We've got 1 minute to spare. Thank you all for your questions in the Q&A and being so engaged. And thank you to our three wonderful people who did our questions tonight and our problems. I think they did a great job. So keep up the good work, everyone, and we'll keep getting in touch with you about the course. Kat will be back and sending you information soon enough. So thanks, great to see you all, and have a good evening. Thank you, bye.